5.4, solving right triangles. Now before we get into right triangles, we're going to talk about significant digits. Now I'm going to go over this. Officially I have to, but to be honest, once we get through this little discussion, I'm going to kind of ignore it. I'm going to ask you just to use a little common sense in how we do this. So basically, here we go. So significant digits, the idea of significant digits is you're saying which of the numbers are really valid in telling you something and which ones are not. And when we're doing calculations, we have to look at those significant digits of what we're starting with and determine whether our answer can be precise to a certain value or not. Now let's say we have three measurements that we're adding together. So we have 21 feet plus 340 feet plus 9.2 feet. So we took these measurements. Without any other indicators, we assume that any non-zero digits are significant. And in this situation, that's a safe bet. So we can assume that this was measured to the nearest foot, this was measured to the nearest 10 feet, and this was measured to the nearest 10th of a foot. So if I add this up, 21 plus 340 gives you 361, plus 9.2 gives you 370.2. feet. But we have a problem with this. And the problem with this is that although this measurement is to the nearest 10th, this one is only to the nearest 10, which means it could be off by as much as 5 feet. If that's the case, does this 0.2 feet really mean anything if one of the measurements could be off by as much as 5 feet? And the answer is no. So we have to look at this and say, well, the least precise measurement was to the nearest 10 feet, so we can only give our answer to the nearest 10 feet. That's the idea of significant digits. Now let's build a little table of how this affects trigonometry and angles and such. So if we have an angle measured to the nearest, and we're going to have that column. I'm going to give an example. And then we're going to give the significant digits that are equivalent to that. So if I have an angle measured to the nearest degree, 47 degrees. That's the equivalent of 2 significant digits. So if we're finding the trigonometric ratio associated with that, we can only give it 2 significant digits. If we have it to the nearest 10 minutes, or 1/10 of a degree, so that could be 49.6 degrees, or it could be something like 48 degrees, 20 minutes. Then we can do 3 significant digits. If we have to the nearest minute, or 100th of a degree, such as 82.61 degrees, or 59 degrees, 72, not 72 minutes, let's make it 52 minutes, 52 minutes, then we can go to 4 significant digits. And then if we have to the nearest 10 seconds, or 1,000th of a degree, such as 56.918 degrees, or 81 degrees, 17 minutes, and 10 seconds, then we can go to 5 significant digits. So now that we've covered that, we can erase it and we can pretty much ignore it for this course. But I do ask you to use common sense. If you're doing calculations and we have sides measured to the nearest hundredth, then your other sides should be measured to the nearest hundredth. If you're doing calculations and your angles are to the nearest tenth of a degree, then your other angles should be to the nearest tenth of a degree. So just use some common sense while you're dealing with it. Okay, so now what we're going to do is we're going to look at solving these right triangles. And let's say we have one angle and one side of a right triangle. So I've got a right triangle here, A, B, C. Sides are A, B, C. And I tell you that angle B is 21 degrees, and that side A is 19.2 centimeters. And what I want you to do is I want you to find angle A, side B, and side C. So how are we going to do that? Well, first of all, we know that angle C is 90 degrees. We also know that angle A is the complement of angle B. So 90 minus 21 gives us 69. So A is 69 degrees. We know that side A is 19.2 centimeters. And we also know these other two angles, 69 degrees and 21 degrees. So let me just put these in place a little bit so we can visualize more. There we go. It just allows me to visualize a little better. If I want to find side B, well, I have 69 degrees, I have 21 degrees. I'm going to use 69 just because it's easier for me to visualize it that way. The tangent of 69 degrees is the opposite A over adjacent B, or actually I'm going to switch to the other one. The tangent of 21 degrees is equal to B over A. So I can say the tangent of 21 degrees is equal to B over A is 19.2 centimeters. So solving for B is equal to 19.2 times tangent of 21 degrees. Let me plug that into my calculator. 19.2. Tangent of 21 degrees is approximately 0.383864. So I multiply those together, and I get B is equal to 7.370 . But notice that A is only to the 10th of a centimeter, so I'm going to make this to the 10th of the centimeter and make it 7.4. 7.4 centimeters. Now to find side C, I have A and B, so 7.4 centimeters. So finding side C is just using Pythagorean theorem. So we have 19.2 squared plus 7.4 squared. So 19.2 squared is 368.64. 7.4 squared, 54.76. Add them together, you get 423.4. So the square root of 423.4, We take the square root of that, we get 20.577. 20.577 to the nearest tenth is 20.6 centimeters. So now we have all the sides and all the angles, and that's called solving the right triangle. So that's if we have one angle and one side. Let me put down the calculator. So let's erase everything but that triangle and say, well, what if we have two sides of the triangle? And that's all we're given. So I know that A is equal to 5.72 feet. C is equal to 8.49 feet. And that's all I'm given. So we want to find angle A, angle B, even though that looked a lot like an A, and side B. Well, how can we do that? Well, first of all, we have two sides, so we can use Pythagorean theorem to get the other side. So C squared is equal to A squared plus B squared. So if I want to find for B, B is equal to the square root of C squared minus A squared, which is equal to the square root of 8.49 squared minus 5.72 squared. Grab my calculator. 8.49 squared is 72.0801. 5.72 squared is 32.7184. When we subtract, we end up with 39.3617. Take the square root of that, and we get 6.274. 6.274. Our sides are measured to the nearest hundredth, so 6.27 is B. Well, how do we find the angles A and B? Well, actually, we can use any trig function we want because we now have all of the angles of the triangle. Sorry, all of the sides of the triangle. So let's just write those in so we can visualize them. So we've got 5.72, 6.27, and 8.49. So we have all those sides. So if we want to find any of these angles, we can just use a trig function. So let's go for angle B just because it's what I happen to be looking at. The sine of B is equal to opposite 6.27 over the hypotenuse 8.49. So if I want B, I can say B is equal to the inverse sine of 6.27 over 8.49. So 6.27 divided by 8.49 gives me 0.7385159, etc., etc. If I take the inverse sine of that, I get 47.605 degrees. And I'm going to round that to one decimal place, so 47.6 degrees. And that was for angle B. 47.6 degrees. For angle A, it's just the complement of angle B, so that's 42.4. 90 minus 47.6 gives us 42.4 degrees. So, solving a right triangle when we are given two sides. So we know how to do it if we have a side and an angle. We know how to do it if we have two sides. Do we know how to do it if we have two angles? The answer is no. And why is it no? Because if all you have are angles and you don't have length of the side, there are an infinite number of possible triangles that can be built with those angles. So, sorry. We just end up with a bunch of similar triangles. So let's look into some applications of this. If I'm looking out and looking straight across the horizon, if we have an angle that goes up from that horizontal, that is called an angle of elevation. If we have an angle that goes down from that horizontal, that's an angle of depression. So angle of elevation, angle of depression, going down. And this gets used quite often when you're dealing with different real-world examples. So let's say I want to find the height of a tree. So let me get this out of the way. So I want to find the height of a tree if the angle of elevation from a point on the ground is 15.5 meters. So I've got this tree, and don't make fun of my tree. So I've got this tree, and 15.5 meters away from that tree, the angle of elevation from that point to the top of the tree is 60.4 degrees. I want to find the height of the tree. Now you may look at this and go, why would I ever want to do that? Well, trust me, there are times when you want to do this. There are times where you may use similar triangles. There are times where you may use something like this. What if you need to determine the height of the tree so that when you cut it down, you know how much space it's going to take up and is it going to fit without hitting a building that's nearby or something else? That could be very important. I've done this, had to do this with a flagpole to determine how long of a rope we needed to replace, or how long of a cable we needed actually to replace it. And so you can use the angle to determine the height of that object. So how are we going to do this? We're looking for the height of this tree, so that's what we're looking for. We know this angle, we know this side, so what trigonometric ratio will relate this angle and these two sides? Well, it's going to be either tangent or cotangent. Now, I know that my calculator works well with tangent, so I'm going to say tangent. So, if I call this h for height, then I can say that the tangent of 60.4 degrees is equal to h over 15.5 meters. So h is equal to 15.5 times the tangent of 60.4 degrees. So I grab my calculator. There you go, 15.5 times the tangent of 60.4. So 60.4, the tangent is 1.76 approximately. Multiply those together, and my height is 27.28 meters, or 27.3 This one was measured to the nearest tenth of a meter, so I'm going to measure that one to the nearest tenth of a meter. So 27.3 meters tall. Pretty good sized tree. That's about 60 feet. Sorry, let me say that again. That's about 90 feet. Let's look at another application. The angle of depression from the top of a 97-foot building to the base of the building across the street, located 42 feet away. So we want to find the angle of depression from the top of a 97-foot building to the base of a building across the street located 42 feet away. So we got another building over here, 42 feet, and we want to find the angle of depression. So that means we want to find this angle right here. So we'll call that theta. Well, if we look at this, we should realize that this angle here is the same as that angle there. Which means that we have two sides of this triangle, or we could say that we know that this distance is the same as this distance here if we were to create that triangle. But again, we have theta, we're looking for theta, we have the side opposite and the side adjacent, so we're going to use tangent, so we could say that tangent theta is equal to opposite 97 divided by adjacent 42, which means that the inverse tangent of 97 over 42 is equal to theta. So theta is equal to, get my calculator again, 97 divided by 42 gives us approximately 2.30952. And then we want the inverse tangent of that, which gives us 66.5878858. So approximately 66.6 degrees. And many times when you're dealing with angles of depression, you put a negative sign there to indicate that it's going down as opposed to up. If it asks specifically for an angle of depression, I wouldn't worry about putting that negative sign in there. But if it asks you what's the angle between something and it's got an angle going down, it's not a bad idea. In applications, if you're just trying to find angles for a triangle, you never have a negative angle in a triangle. So, 66.6 degrees. Let's try for another example. Bearing in navigation. Basically, directions that you're going and the distance that you're traveling. Okay. So you have a ship sailing south by 34 degrees west for 2.5 hours, then turns north 56 degrees west and goes for 3.0 hours. If the ship travels at a rate of 18 knots, that's nautical miles per hour, find the ship's distance from port. So let's do a drawing of this as we look at this again. So in relation to south, the ship travels 34 degrees west. Oops, get over, I've got a 3 there. So 34 degrees west for a time of 2.5 hours. It then turns In relation to north, it travels 56 degrees west. For 3.0 hours. It's traveling at 18 knots, nautical miles per hour, and we want to determine how far is it from its starting point. So we want to find this distance d. Now, there's a lot of things going on here, but the first things that matter are these angles. We got 56 degrees west of north, 34 degrees west of south. Well, if you remember what I showed previously, we can tell that certain angles are the same. In this particular case, since these two lines are parallel, then this angle here is 34 degrees. Because those are alternate interior angles. So we can have those. And what I notice is 34 degrees plus 56 degrees is 90 degrees. So we have a 90-degree triangle array, right triangle, which is good. We can work with right triangles. Now our distance, or sorry, our time is 2.5 hours this direction and 3 hours this direction. So if I use the Pythagorean theorem, then I can determine what the time would have been if they'd gone straight across this one. So I can say that d, or the time of, I'm going to say d sub t, for the time that would have taken to cover that distance, is equal to the square root of 2.5 squared plus 3.0 squared, which is equal to, let me grab a calculator. Got 2.5 squared, which is 6.25. 3 squared is 9. Add those up, we get 15.25. So the square root of 15.25. So that's going to be just under 4. So 3.9 hours is what it would have taken to cover that distance there. We're traveling at 18 knots, so I can just go 18 times 3.9 hours gives us 70.2 nautical miles. If we travel, which would be the equivalent of traveling 3.9 miles at 18 nautical miles per hour. So 72.2 nautical miles. Now one more example. Yet another application. Let me erase this board. So this is called the subtense bar method. It's used in surveying, where they're looking at something. Now let's say we've got point P here, and they're looking out and they're trying to find the distance between 2 points. And they look at this angle theta, there's a distance d, how far away they are from the item, and I'm going to call this point Q. But this distance here from top to bottom is b. And the distance from here to here is b over 2. So it's split in half. So this line that I've got labeled as D is the halfway point. So basically they're looking, and this gets used in surveying, in determining even things like the size of planets or how far away a planet is at a given time. Like we may know that the moon, I know that's not a planet, it's a moon, that the moon is a certain diameter, right? That would be our B. And we can look and we determine the angle between that we have to change between looking at the one side of the moon to the other side of the moon, the other edge, looking at that thing. That's theta. And then we can use that angle, that subtense bar method, that angle, and the knowledge we have about the diameter of the moon to determine how far away it is from Earth. And you may have seen times where the moon seems really large. And you may have seen other times where the moon seems smaller. Now, part of that can be disturbances from the atmosphere, but part of that also is that there are times where the moon is closer to the Earth and where it is farther away from the Earth. So given this, we look out and we find the following. We find that theta is equal to 2 degrees, 41 minutes, and 38 seconds. B is equal to 3.5 centimeters. We want to find D, the distance away from this object. So let's grab a calculator and do some work here. Okay, so first thing I'm going to do is I'm going to convert this degrees, minutes, and seconds to degrees. And I can do that simply by going 2 degrees, 41 divided by 60 is another 0.68333 repeating degrees. And then 38 divided by 3,600 gives you another 0.0105 repeating. So if I add those together, I get 2.6938 repeating degrees. So now I've got it in something I can work with. Okay? I know that B is equal to 3.5 centimeters, but really I want to find this D here, so I need half of B. I also need half of this theta, so I need theta divided by 2. So let's divide that by 2, and I get theta divided by 2 is 1.34694 repeating degrees. If B is 3.5 centimeters, then B divided by 2 is 1.75 centimeters. So now I want to find D. Well, I have this angle. I have the side opposite. I want to find the side adjacent. So I can say that the tangent of 1.3, I'm going to call it 1.35 degrees is equal to opposite 1.75 divided by adjacent D. So I want to get D by itself, so I'm going to multiply both sides by D, and I'm going to divide both sides by tangent of 1.35. So D is equal to 1.75 divided by the tangent of 1.35 degrees. So 1.75. The tangent of 1.35 degrees is approximately 0.0 yeah, 0.023566 approximately. And so I'm going to divide, and I get 74.25856, dot, dot, dot. We head to the nearest half centimeter here. So I'm going to take this out, or to the 10th place. So I'm going to make it 74.3 centimeters. So D is 74.3 centimeters using trigonometric ratios. So that finishes up solving right triangles.